Hi everyone. Addressing your feedback from today, I got a lot of comments or a lot of questions about the two main equations that we were looking at today. One was this, which is giving you the free energy change for a reaction under standard conditions and its relationship to temperature and the natural log of the equilibrium constant. So I had a question which was, I'm confused on the math behind this equation. That K is equal to exp of negative delta G of a reaction over RT and where to apply it. So in terms of when do you apply these equations, the equations, I had a professor once explain this to me, like how you should conceptualize, how you should think of an equation. What does an equation mean? An equation is a way of relating two properties or two variables or two quantities that you might be interested in. So we have spent a lot of time talking about equilibrium constants that determine the preferred concentrations and pressures of reactants and products. And we've also talked about this concept of free energy, that a substance has a certain amount of energy and it also has entropy. If you want to take account both of those, if you want to decide what is the preferential or preferred direction of change for a process. So in essence, if we ever wanted to connect those two together, if we ever want to talk about the energetics of a chemical reaction, and you also want to talk about preferred concentrations and pressures, then you are going to utilize one of these equations. Now, I should specify these are the same equations. That's a one point to make out. Mathematically, these are the same equations, just rewritten. So I'll tell you how I got one from the other. This EXP, so I had a question asking what is EXP referring to? EXP means e to the whatever is in parentheses. So this expression really should be K is equal to e to the minus delta G naught of the reaction over RT. So it's e to this term. I like doing this partly because I just find this to be a little bit easier to write. If I have to put all these terms as a superscript, they naturally get smaller. When it's like, those are the terms I'm interested in, I just need people to know that it's e raised to that. So I do the EXP just because then everything is the same size. Also, if you're ever typing something up on a computer, if you're ever programming a calculation, this is how you would do this calculation. So that's how you would actually type it out. So I have a tendency to write EXP instead of e to the, but anyway, same thing. Anyway, if you want to get rid of an exponential, the way to do that is to take the natural log of both sides. So I can take the natural log of this, natural log of e to the x is equal to x. So this term here should drop, and then I get natural log of k is equal to negative delta G of the reaction over RT, and then if I multiply over the RT and the negative, then I will get this expression. So they are the same equations. One is just written if you want to calculate K in terms of delta G. So if you're given the free energy change for the reaction and you're given the temperature, this is a way to calculate equilibrium constants at any temperature. Or conversely, given an equilibrium constant and the temperature, you could calculate what the free energy change for a reaction would be under standard conditions. So those are the two most common applications of this equation. And then just the conceptual recognition that there is a connection, there is a relationship between free energy and equilibrium constants. And this is a quantification of that relationship. We talked about the general relationship at the beginning of class today. That is, free energy changes become more negative, equilibrium constants become larger. And vice versa, if the free energy change becomes more and more positive, the equilibrium constant gets smaller and smaller. So there's that. how can I determine K when I'm given delta G but not delta G naught? So if you're given, so let's say I'm going to do this separately. If you want to find K given delta G, not delta G naught. And that's a good point, is that, yeah, this equation only relates the delta G naught, so that's referring to the entropy, or the free energy change at standard conditions. What if you're not at standard conditions? How can you figure out the equilibrium constant? Or can you? Yes, you can, because this was the first relationship I gave to people, which is that the free energy change should be equal to the free energy change at standard conditions plus RT natural log of Q, where Q is describing whatever the current conditions are, whether the pressures are at their equilibrium partial pressures, whether they're at 1 atmosphere, whether they're at somewhere in between. This is what's going to allow us to calculate non-standard conditions. That's what we could do. So if I wanted to calculate K given delta G, you would need more information. You would need to know what are those non-standard conditions, what are the partial pressures or the concentrations of the products and the reactants. Then you could calculate, if you had those, then you could calculate this term. And then this whole term, that would be known, assuming you were given those the values of those non-standard conditions. If you're given delta G, then delta G, that's known. And then the only unknown in this equation would be the delta G naught. But if you know the delta G naught, then you can calculate the equilibrium or rather, if you know the delta G naught, then you can calculate the equilibrium constant. So how you would do it, I would say I'd want to solve for these, I would want to solve this equation. I'd want to solve delta G naught is equal to delta G minus RT natural log of Q. So I would plug in whatever my partial pressures or concentrations are, take the natural log times RT, subtract that from whatever the actual free energy change was. That would give me the free energy change under standard conditions, and then once I have the free energy change at standard conditions, I can calculate the equilibrium constant that way. Okay, here's a really insightful question. Are these equations only valid at equilibrium? Are they only allowed to occur, or do they only occur at equilibrium? I would say that they don't. I would say that they are true whether the system is at equilibrium or not. Let me say that again. I would say that these equations are true and they are valid whether or not your system is at equilibrium. These are derived from the assumption that you're at equilibrium, from the assumption that the free energy change was 0, and then you can assert that Q was equal to K. But this is just a general relationship, in the same sense that K equals, let me put it this way, you have the law of mass action. The law of mass action says that the equilibrium constant should be equal to the concentrations of the products over the reactants. Now, this is true, quote unquote, regardless of whether the system actually is at equilibrium or not. That equation describes some hypothetical equilibrium state. And this is also describing some hypothetical state. The K is obviously referring to some hypothetical equilibrium state, and the delta G naught is referring to changes between hypothetical states where everything is at standard conditions, 1 atmosphere of pressure and 1 molar concentration. Regardless of whether the system is actually at those conditions, this is still true. So I would say no, you can use them whenever you want. Yeah. How do you know that the free energy of the liquid, or rather, of the gas, is greater than the free energy of the liquid. So this was in part of the chart that I made today. I did this. I made this chart and I said, okay, right here, that's the free energy of the gas. I was talking about a liquid in equilibrium with its gas. And I said over here, that should be the free energy of the liquid. Your question was, how did I know that the free energy of the gas was greater than that of the liquid? I knew that because I had previously calculated that the delta G of the reaction from standard conditions was positive 8.5 kilojoules per mole. I determined that by looking up the free energies of formation of the gas and the free energy of formation of the liquid. Those free energies of formation are referring, well, let me explain this first. I knew that the delta G of the reaction was positive, so I knew it was going to increase. So the reaction is talking about a liquid going to a gas. So if I'm going from a liquid to a gas, I know that the free energy of the gas has to be higher than the free energy of the liquid, because if it wasn't, then this change here, this change represents the delta G of the reaction under standard conditions. It wouldn't be positive if the free energy of the gas wasn't higher than the free energy of the liquid. So I know it has to be higher, or it has to be greater. Anyway, I guess I'll go off on a little bit of a tangent, not too much of a tangent, but just a little bit. If people are kind of curious, like what's the distinction between the free energy, the absolute value of the free energy, and the free energy of formation. Free energy of formation is saying how much energy do you need to supply. So this would be the free energy, of gaseous H2O. And down here I might have the free energy of hydrogen and oxygen. This energy change here is the free energy of formation of H2O. How much energy do you need to gain or lose in order to get to this actual value of the free energy of water? So again, delta G's of formation, again, are talking about changes in free energy going up to this particular state, and then I can find differences that way. So a little bit of a tangent there. I hope that it hasn't confused or upset people too much. The graph that you were using confused me. Will it be on the test on Friday? No, I'm not going to explicitly ask any questions about the graph. The purpose of the graph is just to sort of visualize the idea, the distinction between, at any time I can talk about some delta G, but the delta G of reaction is specifically referring to opposite ends of this curve, whether you're at your beginning state or your final state at 1 atmosphere of pressure. And the other value of the graph is to sort of visualize why the equilibrium state is the equilibrium state. It's the minimum of the free energy curve. The equilibrium condition is right here, where the slope of the line, the change in free energy, is approximately 0. Any step away from that necessarily means an increase in free energy and is therefore unfavorable. But other than that, no, I'm not going to ask any specific questions about this graph or how to interpret it or how to draw it or anything like that. Okay, another really good question. Can you explain the difference between G, delta G, and delta G naught? Sure, let me do that. Where do I want to do that? I'll do this over here. So G is just the free energy of a system or a substance. It's just however much free energy it happens to actually have. Just like my weight is, let me see if I can come up with a good analogy here. No, I'm not going to be able to come up with a great analogy here, so I won't hazard to do it on the fly. But I will say that, yeah, it's just the actual value of free energy. It's how much it takes into account its actual energy and how it's distributed, how disordered that energy is. So it takes into account entropy, but beyond that, it's still just how much energy something has. Delta G, that's referring to a process. So some change, some process where things, it could be a chemical reaction, could be a physical reaction, could be a substance spreading out, a gas spreading up and filling its container, but some change that occurs. So some process. So there has to be some process, and if there is a process, we say that the free energy of that system could change during the process, and if that happens, then the change in the free energy is whatever your initial free energy was minus whatever your initial free energy was. So there's that. Delta G naught is specifically saying, okay, it is a change, it is for a chemical reaction or for some physical or chemical process, but it's one specifically where the free energies of your initial and your final state, the substances you're dealing with, are all at their standard conditions. So that, again, is referring to the specific process or the specific case when everything is at 1 atmosphere pressure and 1 molar concentration. So delta G naught is a more specialized, it is a very, very specialized case, a specific case when you're looking at changes between like the beginning and end point of a chemical reaction and you're assuming everything is at their standard state. And that's not always going to be the case, but that's the difference between the two of them. Hopefully that clears that up. I would say I'll expand upon this. I'll draw an analogy between delta G and delta G naught. I'll draw an analogy between them and the difference or the distinction between Q and K. The chemical, rather the equations, just the equations for Q and K, they look exactly the same. They're always products over reactants. So Q, the distinction between Q and K is, yeah, you calculate them the same way, but we think of this calculation here as referring to some special case of equilibrium. This expression can be used at any time and can describe the system at any time. This one is only used to describe the system when it's at equilibrium. So there's somewhat of a similarity here. This one is allowed to look at the change from any potential initial state and any potential final state. Doesn't matter what they are. Whether the system's at equilibrium, whether it's not at equilibrium, whether I'm looking at going from reactants all the way completely into products, or maybe just convert a little bit of the reactants into products. What's the delta G for that? This describes any possible change. This one describes a very special case. Now, it's not describing the case at equilibrium, because again, it looks at everything being at the same pressure, 1 atmosphere and 1 concentration. And at equilibrium, that won't necessarily be the case. But yeah, that again is sort of, hopefully that builds upon or helps clarify the distinction between them. Okay, another question I had here, this is an administrative question. Is the final exam on Monday or Wednesday? Because in the syllabus it says Monday, May 2nd, but Monday of that week is April 30th. May 2nd is a Wednesday. Okay, so yeah, that's a mistake on my part. So let me get this, and I should actually probably double check this, but last time I checked this, the exam is going to be either on Monday or on Wednesday, depending upon what section you're in. If you're in my 8 a.m. section, then the exam is going to be on Monday, April 30th. So if you're in the 8 a.m. section, that means your final is going to be on Monday, April 30th. If you're in my 9:10 a.m. section, your final is going to be on Wednesday, May the 2nd. Both of these exams, they are both going to occur at 8 a.m. So regardless of whether you actually are enrolled in my class at 8 a.m. or not, you will be taking the final at 8 a.m., but it'll be different depending upon which section you're in. I don't have a specific question, but will your questions on the exam, are you going to specify between delta G and delta G naught? Are you going to be clear about that so that we don't get confused? Yeah, absolutely. If I'm specifically asking about delta G or delta G naught, if I'm curious about one versus the other, I will use the appropriate one. I will never accidentally ask for delta G when I'm really talking about delta G naught. I mean, it's possible I'll make a typo, but I will try to make sure that that doesn't occur. No, I am going to specify what I'm asking for you so people don't accidentally get confused. Can you explain again why the vapor pressure increases with temperature? Sure. So for this problem, I had asserted that the vapor pressure for going from a liquid to the gas, the vapor pressure should just be equal to the equilibrium constant. That this should be, so we were talking about water as a liquid going into equilibrium with its vapor. For this equilibrium, the law of mass action should just be the partial pressure of the gaseous water, but whatever that pressure is, by definition, that is the vapor pressure. So, then the question is, how can you explain why vapor pressure increases with temperature? So I see here that vapor pressure is proportional to e to the minus delta G over RT. So let me sort of simplify that a little bit, because what I'm really looking for here is some relationship between vapor pressure and temperature. So I'm just going to look at proportionalities here. I just want to know, how does one variable's change affect the change in another variable? So delta G of the reaction, R, I don't care what their values are because that's not what I'm looking at here. So I can just set, if for the sake of argument, I can set this equal to 1 and set that equal to 1, because again, it doesn't matter what their values are. I'm just curious of how does a change in temperature affect the equilibrium constant and the vapor pressure. So I will say that this vapor pressure should go as e to the minus 1 over the temperature. So let's make sure we know where we're going here before we get there. We know instinctively that vapor pressure, or rather, we know that vapor pressure increases with temperature. You heat water up, it gets more steamy until it actually starts boiling, and when the vapor pressure is equal to atmospheric pressure. So we know that as you increase the temperature, the vapor pressure goes up. So let's see if we can rationalize why that's the case. So e to the minus something, that's the same thing as 1 over e to the whatever that was. So this expression is the same as 1 over e to the minus, e to the 1 over t. So here's a question. If I make t very, very large, then this expression as t becomes large, where do I want to write this? I'll do this here. As for 1 over t, as t increases, in the limit that t goes to infinity, this expression goes to 0. So it gets very, very small. So then at the limit that temperature goes to infinity, I have this expression. This expression here is going as 1 over e to the 0. Did I get that right? Let me think about that for one moment. Yeah, okay, we're good. Anyway, 1 over e to the 0 here, this should be equal to, that should be equal to 1 in the limit that t goes to 0, so the opposite extreme here, then 1 over t is going to infinity. Then I have 1 over e to the infinity. E to the infinity here is going to be infinity. 1 over infinity is 0. So these are my two extremes. Either that in the lowest extreme, the temperature is 0, I have negligible value. The vapor pressure should go to 0 at 0 temperature. At infinite temperature, it's going to scale upwards to whatever it happens to be. So I hope that that might be maybe not the best argument, but anyway, this is the way I look at it. As temperature increases, this term is getting smaller. Then I have e to a small number, which means that this whole term is getting smaller. And then I have 1 over a small number, and that means that the whole thing is increasing. So it's a very mathematical argument, I admit there, that I'm trying to make. But generally, more intuitively, the reason why the vapor pressure increases as you increase the temperature is that we think of temperature as being a measure of average kinetic energy, how fast the particles move on average. Vapor pressure is a result of particles breaking away from the liquid and going into the vapor phase. If the liquid is hotter, the particles move more quickly, they are more likely to break away from the pack and go into the vapor phase. And as a result, we expect the vapor pressure to increase as the temperature increases. That's a very conceptual explanation. This is a very mathematical explanation. Hopefully, either one of those makes sense. Okay, a couple other things here. So this is one comment I got that I wanted to specifically address, or not a comment, this is a question I had, and there was a misconception there that I wanted to address. I had this one question, I'll leave this up, which was, you said, meaning me, that if delta G is positive, greater than 0, then that's favorable. And that if delta G is negative, that is less than 0, that it's spontaneous. And your question was, how are these both able to coincide? How can they both be true? I would say that they are, in fact, not both true. This, I would say, is incorrect. That if the free energy is increasing, that is not favorable. That would be the non-spontaneous change. So it is actually an unfavorable process. So you're right to be confused that those two things should not have seemed to be as though they could both be true, and that's because they're not both true. So I don't know if that's because I wrote something wrong or if there was a miscommunication in terms of transcribing notes, but hopefully that addresses your question. Here's a fun question. In this equation, why is it the natural log? Why does it go as natural log? Or better yet, why does the free energy depend on the natural log of the pressure, not just the pressure? I can give you an answer, and it's kind of a hand-wavy answer because the math is very, well, I won't say it's tedious, but I'll be honest, I haven't gone through this explicitly yet. But anyway, so we know that delta G is equal to delta H minus T delta S. So let's say I'm going to come up with some hypothetical process here where I have a gas that's on one side of a compartment and there's no gas on the other side of the compartment. We know that the spontaneous change here is that the gas should spread out and go over to the other side of the other side of the compartment, because that results in an increase in the entropy of the system. increasing the entropy in the sense that the increase in entropy is due to an increase in the number of microstates. So that's K natural log of the number of microstates. If I increase the volume even more gas continues to spread out, or rather the gas continues to spread out even more because there are more microstates associated with a larger volume than with a smaller volume. So I can say here that entropy is proportional to the natural log of the volume, which means that if I have a gas at a certain pressure, changing its pressure or changing its volume is necessarily going to result in a change in entropy. Now, there might be no heat exchange in this process, so there's no enthalpy exchange, in which case we have delta G is equal to negative T delta S. So it's perhaps not too much of a logical leap here that the change in entropy is going to be related to any changes in concentration or changes in pressure. And again, the part here that is evocative, your question is, where does the natural log come from? It comes naturally from the second law of thermodynamics. This is not the second law of thermodynamics. This is a fundamental definition of entropy. It comes from the definition of entropy as going as the log of the number of microstates. The free energy takes into account entropy, and so as a result, changes in free energy are going to be related to changes in entropy, which are in turn related to changes in the number of microstates, which are in turn related to changes in volume and pressure, which is where we get this natural log from. So the origin of the natural log comes from entropy's definition as the log of the number of microstates. The R comes from the fact that K here, when you multiply all this through, K is defined as the gas constant over Avogadro's number. So all of these equations here are specifically dealing with entire moles of molecules or moles of substances. So you would scale all these calculations by Avogadro's number. So if you multiply this by Avogadro's number, those two will cancel, and then it's where you get the RT from. Okay. Oh, here we go. Speaking of R, in the calculation, in the calculation that you were doing, I was confused on how the value of R was obtained. Is it a provided value in the problem? Is it a fundamental constant? Do we have to calculate it? No, it's a fundamental constant. It is the ideal gas constant. It is the same ideal gas constant you all have been dealing with since fall semester. We introduced it in the context of an ideal gas, but the gas constant itself is actually, how do I want to say this? It has deeper or far further reaching consequences than just gases, I suppose is what I'm trying to get at. Case in point, it's involved in determining how energy is distributed in a chemical system, not just how much pressure and volume a particular gas has. So, point being, it is the ideal gas law constant, so it does have a special constant value. I would never ask you to calculate it. I will give it to you on your equation sheet if you need it. So you'll never have to derive it or anything like that. What other questions can be answered with these equations? There's not a, I don't want to say there's not a ton, but it is admittedly, it's one equation, and the equation has one purpose, or one interpretation, which is how do you relate equilibrium constants to energetic changes? Or it gives you a way of relating equilibrium to temperature. You just also need to know what the free energy change is. So there's two things you can get from it. So in terms of what types of questions could I ask, any question where you're trying to ask what's the relationship between equilibrium constants and temperature, you could potentially utilize this equation to answer that. So how does a solubility, how does the KSP for a reaction change as the temperature changes? Well, you need to know what is the delta G, but then you could still figure out a relationship between temperature and the equilibrium constant. So any problem, any chemical system for which you can write an equilibrium constant, whether it's an acid-base reaction or a solubility equilibrium problem or a vaporization, vapor pressure equilibrium problem, any of those you can write an equilibrium constant for. Their chemical changes, so you can talk about how much energy change occurs during that process, and then you can relate both of those to temperature if you would like to. So the point is I don't have a specific question offhand, but they will most be directly related to relating these two terms, free energy and equilibrium. How can the spontaneity of a reaction be determined for non-standard conditions? So let's say, yeah, you have a chemical system. I apologize, I had planned to give an example problem on this during lecture, but we ran out of time. But I will assert that you go back to this other equation, which I gave you all, which is a relationship between the free energy change at non-standard conditions versus what it is at standard conditions, and it goes as RT natural log of Q, where Q is describing what those non-standard conditions are. So your question is, how can the spontaneity of a process be determined for non-standard conditions? Well, if you know what the non-standard conditions are, if you know the pressures and the concentrations and the temperature, you can calculate this. So you would need to know this. If you know the equilibrium constant, or if you're given the delta G naught, then this would be known. Either if you're given K, then you can calculate it, or if you're given it directly, then you can just calculate it here, and then you can calculate delta G. And delta G is what we are using to decide whether something is spontaneous or not. If it's positive, then it's non-spontaneous. If it's negative, then it's, that's supposed to be non-spontaneous. If it's negative, then it's spontaneous. That is what we use delta G for predicting what is the spontaneous change. We don't use delta G naught to make that prediction, whether something is spontaneous or not. We can use delta G naught to decide whether a change is favorable or not at standard conditions, whether it will convert completely from, say, liquid water or does water prefer to be completely in the form of liquid, or does it prefer to be completely in the form of gas, or does it prefer to be somewhere in between, and how far in between? That's what you get from delta G naught. Delta G is just referring to any possible set of conditions. Where should it change in relation to that? Are these equations only applicable to vapor pressure problems? No, they are applicable to any chemical problem where you are concerned with an equilibrium process. This is not equal to the vapor pressure. Rather, this term is not equal to the vapor pressure, it's equal to K. For the specific problem that we were looking at today, K was equal to the vapor pressure, but it won't always be. If I'm looking at a solubility problem, then what I'm really looking at here is a KSP, and it should be equal to my concentrations of my metal anion and my non-metal cation, whatever they happen to be. Then it's going to be relating the free energy change for the solubility of this metal this metal salt, dissociating and turning into its constituent ions. All right, last question here. You at one point said, you verbally wrote that G depends on pressure and concentration. I did say this, depends and then you said G under non-standard conditions is equal to G at standard conditions plus RT natural log of P. How did you get from here to there? I didn't. This is something you really should derive. And you can derive it using some of the arguments that we were making previously. I didn't want to spend a lot of time doing that derivation because I think it's beyond the scope of this class. More important is just the end result. These are the end results. This is sort of a non-specialized case that you can use to get here, but this was sort of like our starting point. And I didn't prove this. I simply asserted this. So you're correct to be confused. How did I go from here to there? I jumped over all of the math, and there is no immediate connection between this and that. But this was the general observation that we made based upon the graph that I showed, was that, okay, as the pressure of the system changed, the free energy changed. So I was basically saying, okay, there is some relationship between the free energy of a substance and its current pressure. And then I simply asserted to the class that this is that relationship. Again, that is something that you would derive in a formal class on thermodynamics. You will do that in Chem 341, or I think it's Chem 341. In PChem, in LMU's chemistry department, you will actually go through and derive this expression. For our purposes, we just need to know that that it's true, and even more importantly than that, we need to know the consequences of this, which are this equation, which is the same as that equation, and then this equation, which is just allowing you to calculate G under any set of conditions. Okay, so that is all the questions for today. It's quite a few, which is great. If you have more, or if I have not addressed your question sufficiently, I would be very happy to answer any questions you have in office hours. Otherwise, hope everybody has a great weekend, and I will see you all on Monday.